Solids of revolution. So what that means in terms of calculus is, suppose that you have some shape, like I'm going to use a piece of a parabola. So this is just part of y equals x squared. And then you take that shape right there, take that area, and of course the area is in 2 dimensions. But then imagine that this x-axis right here could spin around. So you take the x-axis and you spin it around like this. And then this thing is going to go spinning around the x-axis. And it will create a 3-dimensional object. So to show that it's rotating around the x-axis, we put a little circle or arrow like this. So rotate about, you like my Canadian, the x-axis. And then it would make a shape. So a 3-dimensional shape, which right now is sort of hard for me to draw, but it would basically make a mirror image of it going down like this. And then this would all be filled in. And so that sort of looks like a tack or even a Hershey's Kiss. Now what if you take y equals x squared again, so this piece of the parabola, but this time we're going to use the y-axis. So take this region right here and then rotate that about the y-axis. Rotate about the y-axis. So then this would go spinning around like that, and there would be a mirror image of it on the other side. And then it would make a 3-dimensional shape, and it would be sort of like a cereal bowl. But the only problem is the cereal bowl is completely filled in. There's no space for cereal. Okay, so then how do you find the volume of such a thing? Well, before we do that, if you have a right circular cylinder, and I'm going to make a short one like this, so something like a quarter, then find the volume. So the volume is equal to, well, you would need to know the radius, and you'd need to know the height. And then the formula for the volume is that it's pi times r squared times the height. That's the volume of a right circular cylinder. Now when it's a right circular cylinder like a soda can, we call it a right circular cylinder. When it's very short like this, like a nickel or a dime, we call it a disc. Just to emphasize that it's very short, because the ones we're going to use are going to be very short. Now let's put those two ideas together. So for finding these volumes, in total we're going to have 3 methods. This first one is called the disk method. So the idea is that you have some function, f of x right here, between, let's say, a and b, and then this is the area that's going to be rotated, and for this one, we'll rotate it on the x-axis. So rotate about the x-axis. I got so distracted with my about, I almost forgot how to spell axis. So in order to represent this black shaded area, what you could do is use one rectangle. So just like when we very first started finding area with the Riemann sums, you divide it into pieces and then you fill it full of rectangles. But we don't really have to draw each and every rectangle. We can just use one, which is called the representative rectangle. So first of all, you need the delta x, and then if we were going to go through all of the parts, that would be b minus a over n, where there's going to be n rectangles in here. So now, the width of this rectangle is delta x. The height of the rectangle is f of x. So when you take this rectangle and you rotate it around the x-axis, you know what kind of shape it makes? A disk. So with the disk that I just had, it was oriented this way. But the way that our disk is, it's actually oriented this way. So it's basically like if you took a quarter and you stood it up right there, that's what it would look like. So for the volume, of course, volume is equal to pi times r squared times the height. So the height, well, when this disk, when you take it out and you put it on the ground over here so that you can find its volume, then this is actually going to be the height. And if you measure from here up to the function, then that's going to be the radius. So then the radius is going to be the f of x. So that means that the formula becomes pi, the radius is the function, that needs to be squared, and then it's multiplied with delta x. So this is the formula for one of these disks, and then we need to add them all up going from A over to B. Well, that's exactly what integration does. So the total volume is going to be integrate from A to B, and then pi times the function gets squared, and then delta x becomes dx when you're doing an integral. Now, an important couple of notes is number one, the radius. So in these different methods, there are going to be different things. So it's important to note in here. The radius, for one thing, it goes from the axis of rotation to the function. And then the other important thing is, notice that the radius is perpendicular to the axis of rotation. Okay, then we're ready to do an example. So this is example number 1. Suppose you have the function, the square root of x, on the interval from 0 to 4, and then rotate about the x-axis. So the square root of x function would look like this. Go from 0 to 4, and then this, so just lightly shade that part. This is the area that we are rotating, and then rotate that about the x-axis. So when that rotates around, then it would sort of look like the tip of a bullet, because it would be sort of pointy up here. Okay, something. So the representative rectangle goes like this. It's perpendicular to the axis of rotation. And then that means that the radius is perpendicular to the axis of rotation, and it goes from the axis of rotation to the function, and that is a length of the function, which is square root of x. So then we need to integrate from 0 to 4. Pi, the radius gets squared, and then times the height, which is dx. So once you square the square root, this is just going to be x. So all we need to do is integrate x. And the integral of x, or the antiderivative of x, will be x squared over 2. And then evaluate that from 0 to 4. So that is going to be pi times 4 squared over 2 minus pi times 0 squared over 2. And of course, this part's going to be 0. This will be 16 divided by 2, which means that it's 8 pi. So the volume of that object would be 8 pi. And because it's volume, that would be whatever the units are, it's in cubic units. Then for one that is a little more interesting, so for example 2, how about if it's x equals y squared on the interval from 0 to 1, and then rotate about the y-axis. So this problem right here is switching the role of the x and the y. So x equals y squared. What's the graph of that look like? Well, of course, you could just solve for y by taking the square root, and it's actually the same function. It's the square root of x function. Looks like this. But we're talking about the y-axis. So this one is talking about this being the region that we're going to rotate. So take that shape right there and then rotate it about the y-axis. So that, once you rotate it around, again, that would look like a Hershey's Kiss that was sitting on its very sharp point right here. So this time the representative rectangle actually needs to go this way because the representative rectangle needs to be perpendicular to the axis of rotation. And the radius will go from here to here. And right here, it's going to be x equals y squared. So the function is y squared. And so we're going to integrate. And then this is saying 0 to 1, which because the y is the independent variable on this, that means it's talking about y. So y is going from 0 to 1. So integrate from 0 to 1, pi, and then the radius gets squared. And then because we're working with y, this needs to be dy. So this will be y to the 4th. The antiderivative of y to the 4th will be y to the 5 over 5. The pi will stay there. And then evaluate from 0 to 1. So when you substitute a 1 in for this y, that's going to be 1/5. And when you substitute the 0, that's going to be 0. So the final answer is pi over 5. Then, for one that is a little more challenging, you guessed it, trigonometry time. So for example number 3, go with y equals sine of x on the interval from 0 to pi. And since x is the independent variable, that means this is talking about x. And then part A, rotate about the x-axis. So the sine graph would go like this. from 0 to pi. It goes up to a maximum height of 1. And then lightly shade this part. This is what's rotated about the x-axis. So the next thing is draw the representative rectangle. There we go. The rectangle needs to be perpendicular to the axis of rotation, so that's good news. And the radius is going to go from here up to the function. So that means that the radius is equal to sine of x. So next step, set up the integral. So it's going to be integral from 0 to pi. And then the formula is pi, the radius gets squared, and then times the height, which is dx. All right, that wasn't too bad. Now, how do you integrate it? Yes, you're right. We need to use a trig identity for sine squared. So we're going to use the trig identity that says it is 1 minus cosine of 2x over 2. And then before I integrate this pi over 2, I'm going to factor that out. And then it would just leave 1 minus cosine of 2x that I need to integrate. So the antiderivative of 1, that'll just be x. And then it's going to be minus sine of x for the antiderivative, but it's going to have to be sine of 2x since that was cosine of 2x. And then because of the chain rule, the derivative of the inside is a 2, so divide by a 2. And then it gets evaluated from 0 to pi. So then we would have pi over 2, and then substitute the pi, so x is going to become pi. When you substitute pi in here, sine of 2 pi is 0, so that is gone, that's 0. And when you put the 0 in here, that's 0, so that contributes nothing. Also, this would become sine of 0, so that contributes nothing. So the only thing left is that first pi that gets multiplied with pi over 2. So the final answer is pi squared over 2. Now for part B. Part B, take the same shape. So number 3, part B, take the same shape, the sine graph from 0 to pi. So this is the region. And then rotate about the y-axis. Which I will show by putting a little circle thing right there on the y-axis. All right, so draw the representative rectangle. Well, one rule for the representative rectangle is it needs to be perpendicular to the axis of rotation. It actually does not have to touch the axis of rotation, but its direction has to be perpendicular. So then the representative rectangle has to go like this. And then we've got two problems. One problem is there's a gap right here. And we have covered nothing that says what to do if there's a gap. That's a problem. The other problem is, what's the length of this rectangle? To find the length of the rectangle, you have to take the number on the right, and the number on the right comes from sine of x. And then minus the number on the left, and the number on the left comes from sine of x. So that means if you want to find the length of this rectangle, you have to do sine of x minus sine of x equals 0. That's disappointing. So this one we can't even do yet, but I wanted to show you because it's important to draw this rectangle to see if it's even possible with the disk method. So this one, not possible yet, because we can do this one in the next section, but just not yet. All right, then on to the very last idea of this section, and that is, what if there's a hole or a gap? So this is called the washer method. And washer doesn't mean like the dishwasher or the clothes washer. It means like you've got this disc, it's got a hole in the middle, you know, like nuts and bolts and washers, like that. A donut with sprinkles. We should put sprinkles on the donut. Little red sprinkles. Okay, but it's actually a washer. So the idea is actually pretty simple. It's not that much different than the previous section. The previous method. So you would now have two functions, f of x and then g of x. And perhaps they intersect, perhaps they don't. So this could be b, this could be a, this one they're intersecting, this one not, so I just draw a line to close off the shape. And then this is the shape, and we're going to rotate it around. And we're going to rotate it around the x-axis. So basically, you just need to do the disk method and subtract the two answers. Because if you do the disk method with f of x, then that would find all of the volume going all the way down to the x-axis. If you then do the disk method with g of x and you get your answer and you subtract that part off, then that part gets subtracted off and all that's left is that one. So the volume for the disk method is, so you integrate from a to b, and then it's going to be pi, and then for this one, the radius would be f of x, and then the radius has to be squared. And then subtract when you do the disk method for this one, and that means that the radius, g of x, that one gets squared, and then dx. So basically, instead of there just being one function squared, it's going to be the bigger one squared minus the smaller one squared. And then I like to label it as, this one is the big R squared, and then this is the little r squared. So the big R would go from the axis up to f of x. So that's the bigger radius, big R. And then the smaller radius would go to the g of x, little r. Now for an example. This would be example number 4. So one function is y equals x minus 1 squared plus 3. Also, y equals 1. Also, x equals negative 1. Also, x equals 3. And then rotate about the x-axis. So this one right here is a parabola. Its vertex is at 1, 3. So 1, 3, not drawn to scale. And then it's a parabola that goes like this. And then this is y equals 1. So y equals 1 is a line that goes across like this. And then go from x is a negative 1 until x is a 3. So this shaded region, that is what's going to be rotated. And it's going to be rotated about the x-axis. And as you could see, there's this little gap right here. So that means we need to use the washer method. And what I like to do is identify what method I'm supposed to be using And then I write the general formula for it. Just to remind myself, this is how I need to set it up. Okay, so the representative rectangle, it has to be perpendicular to the axis of rotation, so it has to be going this direction, and it should go from one function to another function, never from the same function to itself. So it would never go from the parabola on this side to the parabola on this side. It can go from a parabola down to a line, or a line up to a parabola, but it needs to be two different ones. Then I need to know what's the big radius and what's the small radius. So the big radius goes from here until it gets to the top of the rectangle, and that is when it hits y equals x minus 1 squared plus 3. I forgot this part of the directions. This one we're just going to set up the integral. Okay, so this one is going to be volume equals integrate. So x is going to go from -1 to 3. And then there's going to be pi. And then we need the big radius squared. So I'm working on that part of the formula right now. So the big radius is parentheses x minus 1 squared plus 3. That gets squared. Then for this part, the small radius. So the small radius goes from the axis of rotation until it hits the bottom of the rectangle. So that's just this little gap right here, which no matter where you go, that's always a gap of 1, because this is the line y equals 1. So that means that the little radius is equal to just the number 1. And then that would be integrating with respect to x, so that's a dx at the end. All right, I'll talk to you again soon.